Welcome to today's tech update. We're looking at a landscape that feels fundamentally different from 6 months ago. Today we're tracking 10 major stories, and there's a real through line connecting them: standardization, self-hosting, and this increasingly blurry line between AI tools that help humans and AI systems that operate autonomously. Let me set the stage. We've got Google pushing infrastructure with two different plays: Agentic resource discovery and open knowledge format. Anthropic just dropped a major Claude design overhaul. We're seeing the explosion of local LLM deployments, everything from running models on budget GPUs to spinning them up on Raspberry Pi hardware. NVIDIA's moving into agent security, Databricks is reimagining how you share AI across organizations, and we've got a robotics breakthrough from Anthropic that's frankly startling. Plus a new competitor from Xiaomi nobody was expecting.
Right, and what strikes me is none of these are isolated product launches. These are all pieces of a massive infrastructure reshuffling. You've got Google essentially building a discovery layer for the agent economy. You've got standardization plays from Google, Databricks, and smaller builders, all converging on the same insight. The companies that survive the next phase are going to be the ones whose tools work seamlessly, without lock-in. And then you've got the self-hosting narrative absolutely exploding. People are literally replacing entire stacks of cloud subscriptions with local models running on hardware that costs a fraction of a year's software bills.
That's the pattern I want to dig into today. We've got stories about local LLMs on budget GPUs, browser extensions replaced by Llama setups, Raspberry Pi running sophisticated agents. These aren't edge cases anymore. These are viable architectures. And then at the enterprise end, you've got Google Cloud's agent registry and Databricks building governance layers on top of open standards. It's almost like we're watching infrastructure mature in real time.
Exactly. And the autonomy piece is the wild card. Claude Opus completing robotics tasks 20 times faster than the fastest human team. That's not incremental improvement. That's a capability shift. We're going to walk through what that means for the businesses being built around AI today. But first, let's break down each of these stories properly. We'll start with Google's infrastructure plays, move through the local LLM revolution, and get to some of the more surprising announcements by the end.
Fair. Lots of ground to cover. Let's start with ARD and how Google's trying to wire the entire agentic AI ecosystem together. So Google's ARD, Agentic Resource Discovery, is essentially a discovery layer for the agent economy. Here's the core insight. Organizations can publish an AI catalog.json file on their own domain. That file describes all the tools, skills, and agents they want to expose. Registries, think search engines for agents, crawl these catalogs, index them, and create a searchable ecosystem. The whole thing is decentralized. Organizations own their identity through domain control.
Okay, but what does that actually enable that wasn't possible before? Right now, if I want to find a specialized trading data API or connect to some third-party automation tool, I either stumble onto it through documentation or I'm stuck with whatever my platform integrates with natively. Does ARD change that?
It changes it fundamentally. Instead of siloed discovery, you get cross-organizational discovery without platform lock-in. An agent can search across multiple registries, find the tools it needs from different organizations, and connect to them, all because those organizations publish their catalogs in a standard format. The protocol-agnostic part is clever too. ARD handles discovery and trust verification. The actual execution hands off to native protocols, MCP, A2A, OpenAPI, whatever the service uses natively.
So, it's plumbing. Discovery infrastructure, not implementation lock-in. That makes sense. But how do you actually trust these connections? If I'm an agent connecting to some random organization's API, what stops that API from being malicious or fake?
This is where the cryptographic trust model comes in. Trust is anchored to domain ownership. When an organization publishes their AI catalog.json on their domain, that ownership becomes their identity. Registries or clients verify the publisher's identity before establishing a connection. It's zero trust federation. You don't rely on some central authority vouching for everyone. You verify domain control directly.
That's elegant, actually. You can't fake being someone else's domain. So let's talk about Google's layer on top, the agent registry. Google Cloud isn't just publishing a spec, they're also offering an enterprise product. How does that fit into the open ecosystem narrative?
That's where the tension lives. ARD is the open specification. Anyone can implement it, publish their own catalogs, build registries. But Google Cloud's agent registry is the enterprise flavor. It offers hosted catalog search, governance like URN assignment, egress policies, and agent identity verification. It's sitting on top of the open standard, but with governance controls that enterprises care about.
So the question isn't whether ARD is open. It is. The question is whether Google's implementation becomes so dominant that the open standard becomes almost theoretical. If everyone uses Google Cloud's agent registry because it has the governance features enterprises need, then effectively, discovery is happening inside Google's walled garden.
Exactly. That's the real play. Google's not locking down the spec, they're building the most compelling platform on top of it. And from a business perspective, that's smart. They get to be in the middle of agent connections while maintaining the appearance of openness. Whether other registries can actually compete with Google's governance and scale remains an open question.
All right, so we've talked about discovery infrastructure. Now let's talk about what gets discovered, the actual knowledge and context that agents consume. Google just released Open Knowledge Format, OKF, and it's a vendor-neutral Markdown standard for packaging knowledge that AI agents can work with. Here's the thing. Most people think about AI agent context as just feed it documents. But there's actually a hard problem underneath that nobody talks about much: context engineering. How do you get the right information to the agent at the right time, in a format it can actually use?
Wait, but agents already work with raw documents, right? I can dump a PDF into Claude, I can point cursor at my code base, I can feed anything into a local model. Why does it matter if the knowledge is in Markdown or some special format? What's the friction we're actually solving?
That's the natural question. The friction shows up when you're using multiple tools. Say I'm building something with Claude Code, but I also want to use Cursor for editing, and I'm running a local model on my laptop for experimentation. Each of those tools wants knowledge in slightly different formats. Claude Code might work best with structured context. Cursor expects file-based knowledge. Local LLMs might need everything condensed because of token limits. You end up reformatting the same knowledge base 3 times for 3 different tools. OKF is the answer, one portable format that works across all of them without reformatting.
Okay, that makes sense. But here's my skepticism, and you know I'm going to ask this. Does standardization actually happen when vendors are competing? Google publishes OKF. Anthropic says they'll support it. But do they really? Or does Claude Code get special handling when the knowledge is in some proprietary Anthropic format? We've seen this movie before with other so-called open standards.
That's a fair instinct, but I think the dynamic is different here. OKF is vendor neutral, sure, but more importantly, it's useful for the people building systems. If I'm the type of person setting up knowledge bases across multiple tools, I care about portability more than any vendor's special features. The vendors actually benefit from adopting it because it makes migration easier and reduces lock-in friction. Google's not making money by controlling OKF. They're making money by having good tools that work smoothly with standard formats. That's actually a competitive advantage over anyone trying to go proprietary.
So the bet is that infrastructure standardization creates a rising tide. Everyone adopts OKF, the ecosystem gets easier to navigate, and the winner is whoever builds the best tools on top of the standard, not whoever controls the standard itself. That's a fundamentally different game from what we've seen before.
Exactly. And it connects directly to what we were talking about with ARD. ARD lets you discover tools and agents. OKF lets you standardize the knowledge those agents consume. Together, you've got the scaffolding for an actual open AI ecosystem where organizations can plug their tools in without betting their entire architecture on a single vendor's platform decisions.
Anthropic just shipped a major Claude design update, and it's repositioning the entire product. We're talking design system imports from GitHub, bi-directional integration with Claude code, and most importantly, a fix for a token consumption problem that was frankly alarming. Pro users were burning 80% of their entire weekly token allowance in just 25 minutes. That's not a feature problem. That's a fundamental efficiency issue.
Wait, let's pause on that number because it's actually stunning. 80% in 25 minutes. That means a pro user with a typical weekly budget is basically unable to do anything else after a single design session. So either nobody noticed this was happening, or Anthropic knew and just shipped it anyway. Which was it?
That's the real question lurking underneath this update. The token burn was real, and it was visible to anyone using Claude Design regularly. So there's a tension here about whether this update represents genuine product maturity, we found the inefficiency and fixed it, or whether it's an acknowledgement that the original product was burning tokens wastefully and they're only now addressing it. The fix itself is supposed to be significant, but what actually changed?
That's the technical question I want drilled into. The update brings three major pieces: design system imports, so you can feed Claude your actual component library from GitHub or local files, and Claude builds with those components instead of hallucinating designs. Then there's the bidirectional Claude code integration, where you can use /design sync to pull your local codebase's design system into Claude Design and then hand off to Claude Code to continue the work. Same AI system means no translation loss between design and engineering, but none of that technically explains why token consumption should drop 80%. What was being burned before?
That's the honest answer nobody's explicitly given. My read is that Claude Design was doing redundant work, reanalyzing context on every prompt, regenerating design systems from scratch instead of holding them in context efficiently, maybe rendering and re-rendering components without reusing patterns. The design system imports should reduce that dramatically. If Claude already has your component library, it doesn't need to spend tokens inferring what components exist or debating whether to make new ones versus using existing ones. It just uses what's there.
That makes sense. So this is efficiency through constraint, essentially. You lock down Claude's design vocabulary to what's actually in your system, and suddenly it can't burn tokens on hallucinated components or iterative exploration of design space that doesn't matter. And then the admin controls. That's the enterprise angle, right? Organizations can lock down what Claude Design is allowed to produce.
Exactly. The new admin controls prevent individual team members from overriding brand guidelines or straying from approved design systems. That's governance. From an enterprise procurement perspective, this solves a real problem. Can we control what this AI produces? Answer: yes, at the admin level. You set your design system, lock it in, and Claude Design operates within those constraints. No designer accidentally introducing off-brand colors or unapproved components because they got creative.
And that connects to the design to code piece. If Claude Design is now locked into your design system, and Claude Code picks up the work directly from Claude Design output, you get a unified workflow. Same AI understanding your design constraints, same AI generating code that matches those designs. There's no handoff where a developer interprets the design loosely, or a designer has to review code for design fidelity.
Right. That's Anthropic repositioning Claude Design from a prototype tool into an enterprise brand compliance platform. The original pitch was AI-assisted design. The new pitch is AI-assisted design that your brand team can trust and control. That's a completely different conversation in procurement. One is nice to have. The other is this solves our design to engineering workflow problem and maintains compliance at scale.
And that also explains the timing. This update arrives while Anthropic is on this aggressive 10-week product expansion cycle. Opus 4.8, Fable 5, new alliances with QuickBooks and PayPal, DXC partnerships. They're not just shipping features, they're shipping features that make Anthropic tools viable for actual business operations, not experiments. Claude Design went from prototype to production tool in a single update.
The token fix itself feels like a referendum on whether they're actually ready for production. If pro users are still burning 80% of their budget in 25 minutes even after this update, then nothing has changed except the marketing narrative. But if the efficiency gains are real, then this is Anthropic saying, we've watched how this product is actually used, we've fixed the inefficiency, now it's stable enough for enterprises. That's a maturity milestone.
Okay, so we've been talking about infrastructure standards and governance. But there's a completely different infrastructure conversation happening right now that's equally important. Running local LLMs on hardware that costs a fraction of what you'd spend on cloud API subscriptions. The practical question is simple. What actually works when you're running on a budget GPU with 4 to 8 gigabytes of VRAM? And the answer is, way more than people think, but with hard trade-offs you need to understand.
Before we get into the technical details, let me ask the economic question first. At what point does running local infrastructure actually win on cost versus just paying for cloud API access? Because there's a capital cost to buying a GPU, there's a learning curve, there's the electricity bill. For most small builders, isn't cloud API still cheaper?
That's exactly the right question, and the answer depends entirely on your usage pattern. If you're making occasional API calls, maybe a few hundred per day, cloud is winning on cost. But if you're experimenting heavily, if you're running an agent that makes thousands of calls per week, or if you're building something that needs real-time inference with no latency, local suddenly looks attractive. A GTX 1660 Super costs maybe $300 to $400 used. That's less than a year of paying for generous cloud API usage. After that, it's just electricity.
Okay, so the break-even is somewhere around 12 months of heavy usage. But that assumes you can actually get something useful running on that hardware. That's where quantization comes in, right? That's the real constraint.
Exactly. Quantization is how we make models fit on cheap hardware without completely destroying what they can do. Here's the basic idea. A full precision model stores numbers in full detail. Quantization compresses those numbers. You might go from 32-bit floating point precision down to 8-bit integer precision. That's a 4 times reduction in model size. But it's not free, you lose some capability and accuracy. The trade-off is real.
So if I've got a 6 gigabyte VRAM budget on a GTX 1660 Super, how many parameters can I actually run? And does that number change dramatically based on quantization strategy?
It changes dramatically. At full precision, you're looking at maybe a 1.5 to 2 billion parameter model maximum. But if you quantize to 8-bit, you can push to maybe 6 to 7 billion parameters. Go down to 4-bit quantization, and you can squeeze in models closer to 13 billion parameters on 6 gigabytes. The catch is that each quantization step costs you. The model gets a little less accurate, a little more likely to hallucinate, slower to generate tokens. But for most practical tasks, 4-bit quantization of a 7 billion parameter model is actually solid.
So model selection isn't just about what's the biggest model I can fit. It's about matching the model to the task and then matching the quantization to the hardware. That's a 3-variable problem.
That's it exactly. And this is where most people get it wrong. They see some benchmark ranking and think, oh, I'll run this top-ranked model. But benchmarks don't tell you if that model is overkill for what you actually need. If you're doing bash command generation or simple document Q&A, a 2 to 4 billion parameter model at 4-bit is plenty. But if you're trying to do complex code generation or multi-step reasoning, you need something bigger, and you might need better precision. Real-world testing with actual hardware is the only way to know.
You mentioned real-world testing. What does that actually look like? Has anyone published data on what models perform well at different VRAM tiers?
Yes, and the data is surprisingly accessible. There's testing on GPUs like the GTX 1660 Super with 6 GB, and what you see is things like Qwen models at 7 billion parameters, quantized to 4-bit running reasonably well. But you also see failures, extension creation, and complex code generation where the model just hallucinates, produces bloated code, or loops infinitely. The point is that the same model that works great for some tasks completely breaks down for others. You need tight prompt scoping to keep the model from getting lost and burning through your context window.
Okay, so we're talking about discrete GPUs like NVIDIA cards, but I know there's a whole separate conversation about Apple Silicon and unified memory. Is the VRAM constraint even the same thing?
That's actually a critical distinction. Apple Silicon, the M-series chips, have unified memory architecture, which means the system RAM and GPU memory are the same pool. The practical difference is that an M2 with 16 GB of unified memory can sometimes run larger models more efficiently than a discrete GPU with 16 GB, because there's no data copying between system RAM and GPU RAM. But the rules for what works are different. You can't just take a testing profile from a discrete GPU and assume it applies to Apple Silicon. The memory access patterns are fundamentally different.
So if I'm someone thinking about buying hardware specifically to run local LLMs, am I better off getting a cheap discrete GPU like a GTX 1660 Super, or waiting for a MacBook with Apple Silicon?
That's genuinely task and budget dependent. Discrete GPUs are cheaper per gigabyte of VRAM. You can get 6 GB for a few $100s. Apple Silicon is more efficient, but locked into Apple's hardware ecosystem and higher upfront cost. For pure LLM inference, some of the quantized 4-bit models run faster on Apple Silicon. For development and experimentation, discrete GPUs give you more flexibility and lower entry cost. Neither is objectively better. It's about your constraints.
I want to come back to the user barrier here. You're describing this as viable, but you're also describing quantization strategies, VRAM tiers, model benchmarking, prompt scoping, context window management. Is this something an average person can actually do, or are we still talking about a technical person's move?
That's an honest question. Right now, it's still a technical person's move. The tooling has gotten way better. Projects like Ollama abstract away a lot of complexity. But you still need to understand what quantization means. You still need to match models to your hardware intelligently, and you still need to know how to scope prompts to avoid blowing out your context window. An average user can probably get something running, but getting something useful running that doesn't hallucinate or crash, that requires real knowledge.
So what's the implication here? Is this the infrastructure for a future where personal LLM computing is normal? Or is it a niche for people who already understand the trade-offs?
I think it's actually both. Right now it's a niche, but an expanding one. As tooling improves and people publish better guides on what actually works on what hardware, the barrier drops, and the financial incentive is real. 1 year of Cloud API costs a lot less than a GPU, but year 2 and 3 the GPU keeps working. That math is going to push more people toward local infrastructure, which means more tooling will target that audience, which means it gets easier. We're at the beginning of that cycle. Here's a consolidation story that actually happened. Someone took a hard look at their browser extension stack, Grammarly, video summarizers, research tools, assistant extensions, and realized they were paying subscriptions to multiple vendors for overlapping functionality. So they did a replacement swap, Ollama running locally on their machine, OpenWebUI as the browser interface, and suddenly, the browser becomes an AI client. They ended up with more capability than all those extensions combined, fewer subscriptions, and no pop-ups pestering them every 5 minutes.
That's the ultimate consolidation narrative, I get it. But I have to ask the scaling question because we've been dancing around it all episode. Can an average user actually do this? Or is this still something that requires terminal knowledge and model selection expertise? Because if the answer is you need to be technical, then this isn't a replacement for regular people, it's just another niche tool.
That's the fair skepticism. Let me walk through the actual setup, and you tell me if it feels achievable. You install Ollama. It's a GUI installer, nothing exotic. You run it in the terminal, Ollama serve, then you pull a model. Say Quen 2.57 billion B. That's one command. Ollama pull Quen 2.57 billion B. Then you open WebUI in your browser, and you're interacting with that model through a chat interface. That's the whole setup.
Okay, so the tooling has gotten considerably better since early local LLM days when you needed to manually compile things. But there's still a step where you're running terminal commands and pulling models by name. That's more than clicking an extension install button. How different is that really from just using Grammarly in the browser?
Here's the difference. Grammarly you install once, but you're paying for it every month, and it's collecting your writing. With Ollama, you set it up once, maybe 30 minutes if you're completely unfamiliar with terminal, and then it's yours locally. No subscription, no data leaving your machine, no company analyzing your writing patterns. And the actual usage? It's the same experience. You open the browser, you interact with an AI assistant, but this time it's running on your hardware, not someone else's server.
So the economics win big. You pay once for hardware instead of recurring subscriptions. The privacy win is clear. But what about capability? You're replacing Grammarly, which is specifically tuned for grammar and style. You're replacing specialized video summarizers. You're replacing research tools. Can one local LLM actually do all of those things well? Or are you taking a capability hit to get the consolidation?
That's where the interesting part happens. The person who did this swap actually reported they got more capability, not less. A decent 7 billion parameter model can do grammar checking, writing suggestions, video transcript summarization, document research, all of it. The cloud extensions were specialized, sure, but they were also siloed. Each one does its one thing in isolation. One local model doing everything means you can ask it contextual questions that cross those boundaries. Want to check your grammar while also getting writing suggestions based on the research you did? The local model can hold that context. The specialized extensions can't talk to each other.
So you're not just consolidating cost. You're actually getting better integration because everything's running in one place. That changes the story. But I still come back to the adoption question. How many people are going to go through that setup process versus just accepting the subscription cost and the privacy trade-off?
That's the real adoption barrier. Right now, it's still a move for people who either have technical chops or are motivated enough to spend an hour learning. But here's what matters. The tooling is trending in a direction that makes this easier, not harder. Ollama exists. OpenWebUI exists. Someone could build an installer that bundles both, adds model selection as a clickable choice, and suddenly the barrier drops for normal users. We're not there yet, but the trajectory is clear. So, we've been talking about local LLMs on budget GPUs. But here's something that might surprise you. Running LLMs on a Raspberry Pi is actually viable now. The Pi Agent framework, paired with llama.cpp, shows that you can deploy meaningful AI inference on hardware that costs under $100. That's edge deployment at a price point that actually makes sense.
Okay, I'm skeptical but interested. Walk me through specifics. What models are we talking about here? What tasks can you actually get it to do? And more importantly, what breaks?
Right, so the sweet spot is Quen models in the 2 to 4 billion parameter range. You can run Quen 3.52 billion or Quen 2.54 billion on a Pi and get actual work done. Bash command generation works well. You give it a task in English, it outputs a shell command, execution happens. Light coding tasks too. Simple Python scripts, basic automation, the model handles it. But here's where it gets interesting, and honestly a bit brutal. Try to get that same model to generate extensions or complex multi-step code, and it falls apart. Infinite loops, hallucinated syntax, saving files as Markdown instead of executing them.
So the model knows enough to be useful for simple tasks, but doesn't have the reasoning depth to handle anything complex. That makes sense given the parameter count. But what's the actual failure mechanism? Is it just running out of context, or is it a reasoning problem?
It's both, but the context problem is the practical constraint. The person testing this actually used a 100,000 token context window via Llama server, which is substantial. But even with that, you can see the model getting confused. It loses track of what it's supposed to be doing, starts iterating in circles, or generates code that refers to functions it hasn't defined yet. The real lesson that emerged is this: lightweight models need aggressively tight prompt scoping. You can't just throw a Qwen 2 billion model a complex task and expect it to figure it out. You need to constrain the problem, break it into smaller steps, give it explicit boundaries on what it can attempt.
So prompt engineering moves from nice to have to absolutely critical. You're not just asking the model to do something, you're architecting the prompt so the model doesn't have room to go wrong. That's a different skill set than using a more capable model where you can be looser with your language.
Exactly. And this ties back to something we saw with the Raspberry Pi's minimalist design. The Pi agent framework is deliberately lightweight. It doesn't have all the bells and whistles of something like Ollama or OpenWebUI running on bigger hardware. No fancy re-ranking, no automatic context retrieval, no multi-turn conversation management happening behind the scenes. That constraint is actually a feature. On limited hardware, bloated interfaces just slow you down and eat into your token budget. The Pi framework forces you to be intentional about what you're doing, which actually makes prompt scoping tighter and more effective.
This is making me think about home automation scenarios. If you've got a Raspberry Pi running Home Assistant already, you've got this cheap inference-capable device sitting there on your network, you could deploy agents that don't need to phone home to a cloud API every time they need to make a decision. That's genuinely powerful for scenarios where latency or network availability matters.
That's exactly the use case this enables. A Raspberry Pi running a 2 billion parameter model can make fast, local decisions without any external API call. Boat monitoring? You could run anomaly detection locally without needing a cloud connection. Home automation logic? The agent runs on the Pi, responds immediately, never leaves your network. For small-scale edge deployment where you absolutely cannot rely on external APIs, this changes the economics. The hardware cost is near zero relative to the infrastructure you'd need to build otherwise.
So the practical trade-off is capability for autonomy. You lose the ability to run complex reasoning or multi-step tasks, but you gain independence from external services. For some applications, that's the right choice. For others, it's not. How do you decide if a Raspberry Pi deployment makes sense for your use case?
The decision tree is pretty straightforward. If your task is simple, well-scoped, and needs to work reliably without external dependencies, a Pi with a 2 to 4 billion parameter model is solid. Bash commands, document queue, and simple classification tasks, all of those work. If you need multi-step reasoning, complex code generation, or you're okay with cloud API dependencies, save yourself the headache and stick with larger models in the cloud or on beefier hardware. The minimalist constraints of the Pi framework aren't a bug. They're an honest acknowledgement of what lightweight models can and can't do. Work within those constraints, and you get a remarkably reliable inference engine. Work against them, and you'll spend weeks debugging hallucination loops.
NVIDIA just released NemoClaw, a secure runtime environment specifically designed for running Hermes and OpenClaw agents inside OpenShell. Now, this might sound like infrastructure minutiae, but it actually represents something important about where agent deployment is heading. These are agents running with managed inference, but inside controlled execution boundaries.
Okay, but let's get practical. What security problem are we actually solving here? I can run an agent locally right now. I can point it at my tools, my APIs, my data. Why do I need NemoClaw as this extra layer? What breaks if I don't have it?
That's exactly the right question. Here's the gap. Experimental agents, the ones you and I are playing with on our laptops, operate in controlled environments where we understand the risk. But when agents become autonomous and you want to run them in production, you have a containment problem. An agent with access to your APIs, your databases, your infrastructure, if something goes wrong, if the agent makes a bad decision or gets confused, it can do damage fast. NemoClaw provides sandboxing. It monitors what the agent is actually doing. It controls resource access. You can set egress policies, rate limits, data access boundaries. The agent operates, but not without guardrails.
So this is about moving from, I trust myself not to break things, to the system prevents bad things from happening. That's a fundamentally different security model. And I'm thinking about organizations running local agents on their infrastructure, people who can't afford agents to be loose cannons. They need observability. They need to know exactly what the agent is doing, what it's accessing, whether it's violating policy.
Exactly. NemoClaw bridges that gap between experimental agent demos and production-grade deployment. It's what turns my agent works in my test environments into my agent works reliably in production with monitoring and containment. And that matters because as agents become more autonomous, like what we saw with Claude, Opus, and Robotics, the security infrastructure becomes table stakes. You can't have autonomous systems making real-world decisions without the ability to observe, limit, and contain them. So we've been focused on discovery and context infrastructure, but there's another layer happening at Databricks that's actually reshaping how organizations share AI assets across boundaries. Delta sharing started as a pretty straightforward idea, share data tables without copying them, but Databricks just evolved it into OpenSharing, and it's not just about tables anymore. We're talking models, agents, entire Genie agent experiences, all governed and shared without lock-in. And here's the significant move. It's now hosted at the Linux Foundation. That's standardization at scale.
Okay, but let me push on the practical problem this solves. If I want to share a data table with a partner organization, I can already do that. I export it, they import it. It takes time, sure, but it works. So what's the friction that OpenSharing is actually addressing? Why can't organizations just copy data around the way they've been doing?
The friction is real but invisible until you feel it. First, there's the data duplication problem. If I share a table by copying it, you now have two copies of the same data. If that data changes, we're out of sync. Second, there's the infrastructure cost. If I have a terabyte of data and you want to access it, I either have to send you a terabyte, huge egress costs, huge latency, or you replicate it on your end. Now, you've got duplicate storage. Third, there's the format problem. I might store data in Delta Lake. You might use Apache Iceberg or Parquet. Every format switch is a translation step, and every translation risks data corruption or performance loss. OpenSharing solves all three at once. No copying, no duplication, cross-format interoperability. The data lives where it lives, and you access it directly through whatever native protocol your system uses.
So it's a zero-copy architecture at organizational scale. That's actually elegant. But then you've got two features that seem really practical: Secure Connect and global distribution. Secure Connect eliminates IP allow listing. Walk me through why that matters, because honestly, IP allow listing feels like a solved problem.
It's solved, but it's incredibly painful to operate. IP allow listing works like this. Organization A wants to share data with Organization B. A gives B their IP addresses. B adds those IPs to their firewall. But the minute anything changes, A gets a new data center, migrates cloud providers, adds a new region. The IP addresses change. Now B has to update their firewall. If B has 50 partners sharing data, that's 50 different firewall configurations to maintain. Secure Connect changes that by being a one-time proxy configuration. A and B do the setup once. It works indefinitely, even if A changes infrastructure. No more per recipient IP allow listing nightmare. For organizations managing multiple data partnerships, that's a massive operational win.
And then, global distribution is about reducing egress costs and latency when you're actually accessing that shared data across regions or cloud providers. So, if I'm in Google Cloud and my partner is in AWS, the data can be replicated to the region where I'm actually using it. So I'm not paying egress costs every time I query something across cloud boundaries. That's a real cost reduction story.
Exactly. And here's where it gets interesting. Databricks has built OpenSharing to work with a whole ecosystem of on-premise and private cloud storage. MinIO, Cumulo, Vast, Cohesity, NetApp, Nutanix, all of those storage systems can participate in OpenSharing. That means if you've got data locked in your own data center on NetApp storage, you can still share it with external partners without moving data to the cloud. The portal stays on your infrastructure.
Okay, so we've talked about data sharing getting frictionless. But the really interesting innovation is what happens when you share Genie agents themselves. This isn't just about sharing tables or models. This is about sharing entire governed AI analytics experiences. What does that actually mean, and why is that a governance innovation?
This is where OpenSharing moves from data infrastructure into AI monetization. A Genie agent is a governed AI analytics experience. It's an agent that you've trained on your data, tuned to your business logic, locked down with specific capabilities. Instead of just sharing the raw data or even the model weights, you can share the agent experience itself. Your partner can interact with that agent, ask questions, get answers, all within governance boundaries you control. You can set prompt quotas. You can limit the number of rows it returns. You can track usage and charge based on actual consumption.
So you're not selling the raw data or the model. You're selling the intelligence product. That's a completely different business model. Your partner doesn't need to understand your data schema or worry about what queries might break things. They interact with a governed agent that can only do what you've allowed, and you can monitor everything and charge per interaction if you want. That's productization of AI workflows.
Exactly. And it connects back to what we were saying about ARD and context discovery. You've got organizations discovering each other's capabilities through open standards. You've got standardized formats for knowledge and context. And now you've got a way to share not just data or models, but entire governed AI experiences across organizational boundaries, with usage-based monetization controls built in. The entire stack is becoming interoperable and open, but with governance that enterprises actually care about.
This also ties back to something important we saw throughout today's stories. Google's ARD lets agents discover tools across organizations. OKF standardizes how knowledge travels between tools. Claude Design and Claude Code handle design to engineering workflows. Now Databricks OpenSharing is about sharing AI products, the actual intelligence services, across organizational boundaries. These aren't isolated features, they're the infrastructure for an actual AI economy, where organizations can collaborate, share, and monetize without being locked into a single vendor or platform.